So we were discussing gravitation chapter. Last class, we saw the variation of acceleration due to gravity. We saw what is acceleration due to gravity in the first place. Then we saw how it varies with respect to altitude, right? So with respect to altitude, there were two formulas that I told you. One is GME divided by RE plus H the whole square, and the other is G into 1 minus 2H divided by RE. Right? So in today's class, what we are going to see is, we will see the next important topic, that is, write on the heading, it's called gravitational potential energy. So write down.
Sir, that symbol is U, sir.
It is U. Okay. So we know what is potential energy, right? We have already discussed this. We have seen what is gravitational potential energy, and its value is mgh, right? So the question is it going to be mgh every time? The answer is no, because you can take the gravitational potential energy as mgh, where g is 9.8 meters per second square, only if the object is taken closer to the surface of the earth. Only if the object is on the surface of the earth or closer to the surface of the earth. What will happen if the object is at a different location, right? At that time, how are we going to deal with it? So listen. So the alternate definition that we are going to give is, we know that potential energy always is related to the position of the object. Okay. And I have already mentioned that wherever you see the term energy, energy means work done. Okay. So the gravitational potential energy, write down the definition for it. So the definition is like this. It is the amount of work done in bringing an object from infinity to a given point in the gravitational field of another. I'll explain what it is right now. So work done in bringing an object from infinity to a given point in the gravitational field of another. So that is the basic definition of gravitational potential energy. Okay. So let me explain what this infinity means. So till now we were discussing, if there are two masses m1 and m2, let's say they are separated by a certain distance, then what is going to exist between them? There is going to be a force of attraction existing between them, which is given by the formula F is directly proportional to m1 into m2 and inversely proportional to r square, combining we write it as g m1 m2 by r square. So this is a known fact. So till now what we were doing is, we were discussing only in terms of the force between both the objects. Now let's think of one basic aspect. So if there is a mass, okay, so I'll give you another way to understand this. Suppose you can imagine this, okay. Suppose I have a bar magnet in my hand. I have a north pole and south pole, and I'm keeping an iron particle close to this magnet. What will happen?
It will get attracted.
The iron particle will get attracted to it, right? That's what we are going to observe. But if I ask you what exactly is happening around it, can I say, like, when this magnet is present, see this concept, guys, there is an imaginary region around this magnet, which we call it as, what are these lines that I'm drawing?
Magnetic field.
Magnetic field.
So I'm drawing the magnetic field line. So can I say that around this magnet, there is something called as magnetic field that is existing? And the iron particle was brought into the effect of magnetic field due to the existing bar magnet, accepted? Right? It is due to which the attraction is taking place. In a similar way, instead of talking about bar magnet, what we are going to do is, I'm just creating a similarity, okay? So wherever there is mass present, okay, listen to it. Wherever there is a mass present, around this mass, there will be an imaginary region which is called as gravitational field. Like how around a magnet you have magnetic field. Suppose you have a charge. Around the charge, there will be something called as electric field that will be existing that you will learn next year. But you just know the name. So charge will have electric field. In a similar way, mass around it will have something called as a gravitational field. Gravitational field is nothing but an imaginary region around the mass where you try to bring another mass, it will get attracted. The other mass will get attracted. You're able to understand? Similarly, around M2 also, there will be an imaginary. You can't see it, but you can feel it. For example, you say you're dropping some object, okay? You're holding it. If you drop the object is going in the downward direction. So at that time, what you can say is, let's say your hand is like this, and you have a ball in your hand. And when you drop the ball will go in the downward direction because it is experiencing a force of mg, right? So what the other way of telling is, you can say that the ball which you had in your hand is moving under the influence of the gravitational field due to Earth. Okay, the gravitational field, you can't actually see it, but you're able to sense it. You're able to see that the ball is moving. Are you guys able to understand? Yes or no?
Sir, could you repeat?
Sorry?
Could you repeat, sir?
Which point?
The ball.
See, you have a ball in your hand, you drop it. Okay, let's say you're holding something in your hand, you're dropping it. It is going to move in the downward direction, right?
Yes,
The
sir.
question is, the ball has some mass m. Can I say the ball has a region around it which you are actually not able to see? And what is that region called as? The region is called gravitational field, which is actually trying to pull the ball which you had in your hand when you leave it. You're actually not able to see it, but you're able to sense it. That's what I'm saying. That is why I told it is an imaginary region. I had to explain all these things because there is a term here, gravitational field of another. Okay. So if you understand what is gravitational field, I will proceed with the derivation.
Sir, here
Shall I
you
proceed?
told the ball is attracted to something, no, sir? That's the earth, right?
Yeah, it is attracted towards the center of the earth.
Okay, sir.
Now listen. So here there is a term that is given, infinity is given. So infinity doesn't mean it's a very far distance. Okay. Suppose you have a mass in your hand, then around this, the imaginary region will get extended only till a certain point. Okay, the meaning of it is, if I try to place another object M1 here and M2 here, okay, I have two objects in my hand. I'm placing M1 inside the circle and M2 outside the circle. Actually, it's a sphere. Okay. Now tell me which one will experience force.
M1 will experience.
M1 will experience force because M1 is within the gravitational field of M, whereas M2 will not experience force because it is out of the gravitational field of whom? Of the mass M. Okay, so this M2 is what is said to be at infinity. So infinity with respect to gravitational field means it is a point outside the gravitational field. It doesn't mean it's a far distance. Okay, so don't get confused looking at the word infinity. Okay, now see. I will draw all the required diagrams. Suppose you have Earth. Okay, let's not take Earth as of now. Let me take two random particles. Okay, let's say there is a particle of mass m1 which has a gravitational field around it, and there is another particle m2 which is outside the influence of gravitational field. So what are we trying to say? Definition is work done in bringing an object from infinity to the point within the gravitational field. Here an important note to be made is object should be moved as slow as possible. Okay, means it should not have velocity at any point. At every point it should be moved as slow as possible. Now listen to this. Okay, let's say, so concentrate. There is a slightly tricky derivation. Concentrate. Let's say the mass m2 is moved into the gravitational field of m1 and separated by a distance x. Okay, so when it is separated by distance x, m1 is like this, m2 is here, and the distance of separation between them is x. So I want you all to write it along with me. Is that clear? Now see. Let m2 be further moved towards m1 through a distance dx. Okay. So now tell me, what will be the force between the particles in this case? It will be G m1 m2 accepted. So in this case, the force between the particles is G m1 m2 divided by x square. Right. When m2 is further moved by a distance dx, then can I say work done by the force in the displacement of dx is dw is equal to, I'm writing dw because the displacement is very small, f dx. Okay, so you know this formula, dw force work done is equal to force into displacement. That's what I wrote. So what is the value of force, guys? It is G m1 m2 divided by x square into dx. Accepted? Is there any doubt till this step?
No.
So this is the small amount of work done. So now I'm saying work done to move the particle from infinity to some distance r is given as W is equal to integral of G m1 m2 divided by x square into dx. From where to where? From infinity to r. So what I did here is integral of infinity to r. So infinity is the initial point, r is the final point. Okay. Now see, W will be equal to G m1 m2 into integral of dx divided by x square from infinity to r. So that will be G m1 m2 into integral of dx by x square is minus 1 by x from infinity to r. Reason being integral of x power n dx is equal to x power n plus 1 by n plus 1. You people figure out here the value of n is minus 2. Okay. So once you get Gm1 m2, then minus 1 divided by, in the place of x, substitute upper limit, minus 1 by r, minus of minus 1 by the lower limit, that is infinity. So the final answer will come out as minus G m1 m2 divided by r. This is the work done. And remember, this work done is what is going to get stored in the form of gravitational potential energy.
Sir, why is the value of n minus 2, sir?
You find out, no? What is there here?
Okay, sir.
So this is for you to figure it out. Got it? So this is an important formula to be remembered. So wherever you want to understand what is gravitational potential energy, it is always the work done from infinity to some point within the gravitational field of another. Okay? So listen. So this is all about gravitational potential energy. The next term that we are going to see is gravitational potential. So gravitational potential is defined by the symbol V. So this is something similar to what you have learned last year. You would have learned electric potential, right? So it is something similar to that. So observe the definition carefully. Just a minute, guys. So write down the heading. So the heading is gravitational potential. It's called defined with symbol V. So the small change that is going to occur is, the definition is almost the same except the fact that work done per unit mass in bringing an object. Okay. So potential and gravitational potential energy means work done. Gravitational potential means work done per unit mass. So this is the thing you need to understand. Except this, everything else is the same. So when you apply this concept, we can directly write gravitational potential like this. So V is equal to the amount of work done per unit mass. So W divided by M2. What is the value of W that you got? Minus G M1 M2 divided by R divided by M2. M2 and M2 will get cancelled. Minus G M1 divided by R. So this is the formula for gravitational potential. So try to understand. For you to define potential energy, you need two masses. Whereas for you to define gravitational potential, you need only one mass.
So is this the work done by the body which is attracting the other body?
Yes, it is the work done by gravitational force. It is work done by gravitational force, not the external force.
Okay.
What you told is right. Okay. So tell me, guys, what will be the SI unit for this? Work done is measured in joule per mass is measured in kilogram. So joule per kilogram is going to be the SI unit. Okay. Got it? Any doubt, guys?
No, sir.
No, sir.
So for you to understand this concept, what I'll do, I'll give you a very simple problem. Observe. So there is a system like this. There are four masses, each of the same value m. Each of same value m. Listen to the question carefully. They are placed at the vertices of a square. Okay, they are placed at the vertices of a square of side A. Clear? Now you need to calculate two things. First, calculate potential, energy of the system. Second, calculate potential at the center of the square. Okay. So these are the two tasks that we are supposed to do. One is we need to calculate the potential energy of the system. Second is we need to calculate the potential at the center. Here, guys, before we proceed, I just want to explain one important point. Whenever the context is about potential energy, I'm not speaking in terms of questions, okay? Because this concept is important. So whenever I speak about potential energy, it is defined between two masses. That is a preposition used. So potential energy can be defined between masses, whereas potential is defined due to a mass. So wherever the question is about potential, the keyword that will come is at. Because they cannot frame a question, they cannot frame a sentence like this: calculate the potential between the charges. That's wrong. Between the charges, what can you calculate?
Energy.
You can only calculate energy. Whereas due to a charge at a location, if the preposition at comes, then we are going to calculate only potential. Or they cannot frame it like this also. Calculate the potential energy at this particular point, because energy doesn't exist at a point. Okay. So it is very, very simple. I will do this problem, concentrate. So what is the formula for potential energy? U is equal to minus G M1 M2 divided by R. So instead of remembering it like a formula, you can remember like this: minus G times product of masses divided by the distance of separation between them. Okay. Similarly, what is the potential due to a mass? It is minus G M1 divided by R, where M1 is the mass which is producing the potential, R is the distance from the mass to the point where the potential is to be calculated. I hope these 2 points are clear. Right? So now observe 1, 2, 3, and 4. So for potential energy of system, when you want to calculate the potential energy of system, it is calculated how many charges, how many masses are there?
4 mass.
4 masses, right? So when 4 masses are there, how many terms do you come? So you can calculate the potential energy between 1 and 2, and you can calculate it between 2 and 3. Continue.
3 and 4.
You can calculate between 3 and 4, and you can calculate it between 4 and 1. Don't write it as 1, 2, and 2, 1. 1, 2, and 2, 1 are the same. Okay, is that all?
We can't have between 2 and 4 and 1 and 3.
That's what I was expecting. You can. So you'll calculate it between 1 and 3 and 2 and 4 also. So whenever you have masses and they are separated by distance, if you have not used them in the expression, we can do it. So how many terms are there? There are 6 terms in the expression. But how many masses are there? There are only 4 masses. Right? So what is the potential energy between 1 and 2 according to this formula? It is minus G into, what is the mass present at 1? It is M. Mass present at 2 is also M, divided by, what is the distance of separation between them guys?
A.
A. Right? Between 2 and 3. Same thing, minus G M square by A. 3 and 4. Same thing. 4 and 1. Right? Plus, what is the potential energy between 1 and 3? Minus G into M square divided by, what is the distance between 1 and 3 guys? Is root 2a, because it's the length of a diagonal. Minus, what is the potential energy between u2 and 4? It is the same, minus gm square divided by root 2a. So all these added together, you will get minus 4 times gm square divided by a, minus these two added together, you will get 2 gm square divided by root 2a, which implies it is minus gm square divided by a into 4 plus root 2. So this is the potential energy of the whole system. Is it clear, guys?
Sir, why you didn't execute that the formula of gravitational potential energy in all the 4 equations, sir? You just executed.
That's what I included the same. Why didn't I apply? I applied it everywhere. That's what I used, no? Minus G M1 M2 divided by R. See, both the masses are same. M into M is M square. That is why I directly wrote it as M square. Okay, minus gm square divided by a into 4 plus root. Clear, guys? So, next is you need to calculate the gravitational potential At whom? At center. So 4 masses are there. A. Tell me what is this distance?
Root 2a by 2.
That is A by root 2. Right? This half of the length of the diagonal. That's right. A root 2a by 2, or you can write it as A by root 2. So the total potential of the system will be equal to potential due to the first charge plus potential due to second plus potential due to third and potential due to the fourth mass. So what is V1, guys? What is the formula? Minus G into whatever mass you're taking into consideration divided by R. R means the distance from the mass to the point where you're calculating the field. So minus G into M divided by A by root 2 minus Gm divided by A by root 2 minus Gm divided by A by root 2 minus Gm divided by A by root 2. Right? Did you guys understand how I wrote? So first mass is M. From the mass to the point, the distance is A by root 2. Similarly, second mass is M. The distance is A by root 2. So that's how it keeps on going. So minus 4 times Gm divided by A by root 2, which implies it is minus 4 root 2 Gm divided by A. Got it?
Yes.
1 minute, sir.
Yeah, copy it.
So instead of writing the V formula, that is the gravitational potential formula 4 times, you can just write it 1 time and cross it with 4, no, sir?
You can do that, but you should know why 4 is coming. Since this is the first problem, I wrote it those many times. If you know that it is 4 times, just you can write it.
So wrote, sir.
Done?
Yes,
Okay.
sir.
So, the next concept that we are going to discuss. So, there are 2 small subtopics that are left out, which are very, very simple. So, the one which we are going to discuss now is called as escape velocity. So, escape velocity is given by the formula BE. Okay. So, write down the definition for it. So, what do you think? Before that, what do you think is escape velocity?
Velocity
Suppose-
required to escape from the field of gravity.
Very good. That's it. So, let's logically think. If I have a mass on the surface of the Earth, what will it experience? It will experience a gravitational pull in the downward direction, which is mg. Right? Now, my objective is I want to give a velocity to this particle, which I call it as escape velocity, so that this particle is going to infinity. Now, you people know what is infinity. Let's say due to Earth, the field is acting till this point. I should give it a velocity in such a way that it goes out of infinity. Accepted? Guys, yes or no?
Yes, sir.
Okay. Now write down the definition for it. So definition. It is a minimum velocity. It is a minimum velocity with which an object must be projected. It is a minimum velocity with which an object should be projected in vertically upward direction. In vertically upward direction, so that it escapes the gravitational field. So that it escapes the gravitational field of Earth.
Sir, can you repeat it?
Yeah, repeated. So it is a minimum velocity with which an object should be projected in vertically upward direction, so that it overcomes the gravitational field of the Earth. Okay. So that is the definition. To calculate it, it's a very, very simple technique. Observe. For calculating escape velocity, the theory is like this. Kinetic energy of the particle, or I can say like this. Gravitational potential energy of the particle should be converted to kinetic energy. Okay. So G capital M into small m divided by R is equal to half into m into VE square, where m is the mass of the particle and where small m is the mass of particle, capital M is the mass of Earth, capital R is radius of Earth. Okay, so M and M will get cancelled, which implies VE is equal to 2G capital M divided by under a root. So this is the mathematical expression for kinetic for the escape velocity. So if you have a doubt of why I wrote G mm divided by R, it is very simple. So here the mass is m, and we know that the mass of the Earth is concentrated at the center. What is the distance of separation between them? It is r.
So this is from the surface of the Earth, no, sir?
It is from the surface of the Earth, yes.
So if it's in the air, sir, and it's suspended at a height, then it will change the formula.
Then this should change, no? But generally, what does the definition say? Minimum velocity with. So what is the definition I gave you? So actually, you can add this point. It is a minimum velocity with which an object should be projected from the surface of the Earth. Because we are deriving this like a general formula, but your question is valid, yes. If suppose the object is thrown from a certain height, then in the place of r, you should write it as
H, sir.
r plus h. See, if it is at a height h from the surface, if it is like this, okay, if suppose from here you are projecting with VE, then it would have been r plus h. Got it?
Okay, sir. Understood.
Okay. So it is always the distance between both the masses. That's the thumb rule in this chapter, nothing else. So VE is equal to root of 2m divided 2 into gm divided by r, or VE can also be written as root of 2 into gm divided by, I'm dividing with r and multiplying back with r. So what is gm divided by r square, guys? Last class we discussed. It is root of 2 into acceleration due to gravity on surface of Earth. Since right. So this is the value of escape velocity. So there are two formulae. You can either use root of 2g capital M divided by r, or VE is equal to root of 2g into capital R. Okay. By substituting g is equal to 9.8 meter per second square and r is equal to 6,400 kilometer, what we get is we get the value of escape velocity as 11.2 kilometer per second. So when you project an object with a velocity of 11.2 kilometer per second from the surface of Earth, it will never come back. So in a similar way, for different planets, it will change because the value of g will change.
Sir, kilometer per second isn't universal, no, sir. How can we use it?
How can we use it? Means
It isn't universal, no, sir.
no, it is. This is the way escape velocities are defined.
Oh, no, sir. In the MKS CGS units.
No, nothing like that.
Okay, sir.
So
Okay.
for escape velocity, this is the unit used.
Okay, sir.
Okay.
So for every particle, irrespective of mass, this will be the
Yes, yes, because
escape velocity.
escape velocity is independent of mass. No? It is independent of the mass of whom? Mass of the particle. Okay. Am I clear till this point?
Yes.
So this is all about escape velocity. So there is one last concept that is left out, which is orbital velocity, which is called V naught. So this one I will discuss tomorrow, and we can end this chapter. With this, the chapter will get over. Okay. So is there any other topic that you have doubt from today's discussion? Or any other previous topic which you studied you couldn't understand?
So in the physics test, I had a doubt, sir.
Yeah, what was it?
The splitting of something from in a laboratory.
Me also, sir. I didn't even attend that question itself, sir.
Splitting of?
Nucleus. That question.
Nucleus in a laboratory.
I already told you, wherever there is disintegration of nucleus taking place, there is always energy, conservation of momentum. If you have the question paper, can you please read the question alone? Wait, I'm opening from my end. I got it. Wait.
Sir, I got it, sir.
I opened it. Which question is it? 12th question, right? Yeah. So nucleus is at rest in a laboratory. Forget about the word frame of reference. show that if it disintegrates into two smaller nuclei, the products must be in opposite direction. Actually, the products should be for whom? Products of momenta. So what they are trying to say is there is a nucleus, let's say it is of capital mass M, which is initially at what value? Rest. So this is clear, right? So it gets disintegrated. That is happening because of the nucleus instability. So generally this kind of a process is called as radioactivity. Okay, the disintegration of nucleus into its subatomic particles. So when this happens, what is happening? There is a particle of mass M1 and M2 which are getting randomly split. I don't know in what direction. Let's say with velocity v1 and v2. Is it clear till this step?
Could you explain what is laboratory frame of reference?
Which one? Laboratory means lab. In your lab,
So in the lab.
in the lab, yes. Laboratory means lab. In your lab, you're doing this. You're observing this kind of an activity. You have a nucleus which has got disintegrated. Generally, you cannot observe it. Okay, so there is a nucleus which is getting split into its subatomic particles. So laboratory means lab. So frame of reference means that particular. I can say it like you can, as of now, I can tell it's like a coordinate axis. If you assume your lab, you're standing here, you're at a particular location, right, with respect to the corner of the room. Then that particular square, you can call it as the frame of reference. So forgetting all these words, what you can do is a nucleus is at rest. Show that if it gets disintegrated into two smaller nuclei, then the products must be in opposite directions. So what is the initial momentum of the system? Capital M into 0 is equal to, what is the final momentum? It is M1 into U1 vector plus M2 into U2 vector. Is this clear? So what did I apply? I applied the law of conservation of linear momentum, because here it is happening naturally. So wherever you see this nucleus disintegration, the thing that is supposed to come to your mind is law of conservation of linear momentum. So 0 will be equal to M1 into U1 vector plus M2 into U2 vector. So from this, can I say M1 into U1 vector is equal to minus M2 into U2 vector? So this is the meaning of products being in opposite direction, because there is a minus sign. Are you able to understand?
Okay, it's understood.
Yeah.
But sir,
So it's
here
okay, even
you
if
wrote V1, so it should be M1 V1, no, sir.
Sorry, V1. Explanation process I wrote down. Is M1 V1 and M2 V2. So M1 V1, M2 V2. So M1 V1 vector will be equal to minus M2 V2 vector. So the minus sign indicates that they are in opposite direction.
Understood, sir.
Okay. Anyways, see if this question comes next time, ensure you're doing it, because I think it's a textbook problem. It's an NCERT problem. So next time, if it comes in your exam, ensure you're doing it right. Any other problem, guys? Is there any other problem which was tough?
No,
No? That's good. Okay then. So just wait for a minute.